Cool. Before I show you this paper, this is a paper we're going to be talking about, and it's like the first four words of the paper really talk about what the contribution is from a practical point of view, which is the model that's being proposed. It has two benefits. One, it's built explicitly to well, first of all, the models that are being proposed here, they're addressing sequence to sequence problems. So like a really common sequence to sequence problem is translating between languages. So for example, going from English to Spanish. But there's quite a few other ones you could think of, like for example, taking audio and transcribing it so that you would be able to, like, for example, automatically generate subtitles, or possibly taking like a description of an image and making the image and then using that to make a video if you have a sequence of descriptions. So those are audio-visual are really common ones. I'm sure you can think of so many others. Like what would be a good one? Maybe another interesting one, which is, so I have a background in robotics, so that's why I just came to this, would be like taking like force, like the movement of a finger, and trying to translate that into like what the forces would be from that finger. So you could like use telepresence to do like really detailed surgery. So there's a lot of there's a lot of sequence to sequence problems out there, and this model is addressing sequence to sequence problems. And so it has two benefits over existing models, specifically over like the best performing models, which are generally transformers or their variants. One of them is that it's both more computationally and memory efficient. So that's why it says efficiently modeling in the title, which, and it's not a little, it's quite a bit more memory and computationally efficient. And then the other thing that they do is that they specifically tailor their models for handling long-range dependencies. So in a sequence. So what would be a good example of a long-range dependency?
Summarization of a book. Say War and Peace, summarize it.
Yeah, that's a good example. So maybe like details very early in the introduction are only used like much later in the book. And so if you're trying to summarize it, you need to be able to take parts of like chapter 1 and integrate them into chapter 20 in order to get a good summarization of chapter 20 that makes sense. So yeah, it's focusing on long-range dependencies, but the experiments show that even on problems where there aren't long-range dependencies, this model still performs at or near state of the art. So that's the other component of it, is that, and we'll go over the experiments, but basically there's this set of benchmark tasks called long-range arena, where there's like all these tasks that you can train a model to perform, which are trying to check if the model is good at finding long-range dependencies. And so this model is able to actually accomplish a task which no other model has been able to accomplish before in the long-range arena, and also perform better on all the other tasks than pre-existing models. So yeah, those are the two things. So this is a sequence-to-sequence model. It's more efficient in terms of memory and computation, and it's better at modeling long-range dependencies. Yeah, I like to give a summarization at the beginning, so that's why I'm talking so much without going through the paper. But in terms of like the actual, and like a useful one, hopefully, in terms of like the actual, when it says efficiently modeling, there are cases where it's not as good as transformers or like the state-of-the-art models for the task. So there are cases where if you use it, you're actually compromising efficiency. You're compromising performance for efficiency, but also in a lot of the tasks, in the experiments at least, you'll get like state-of-the-art or better than state-of-the-art performance while getting better efficiency. And that's why a lot of people in ML supposedly consider this to be a big like step forward. It also has a lot of cool math, which comes from control theory, which we'll go over now. So that's like a short introduction. One last detail which I would like everyone to keep in mind is, or two things. One, the new model that's being proposed is essentially like a new layer in a neural network. So it's a layer, and the specific part where all the math is like the part of the layer that's going from one sequence to another, from sequence to sequence. And the math that they use, all of the math that they use relies on these sequences being one-dimensional. That's not very obvious in the paper, I think, but maybe it is. So right now, if you have like a sequence that is more than one dimension, for example, like language embedding vectors tend to be like hundreds of dimensions, what you would have to do is have a separate one of these layers, or like this component of one of the layers they're proposing for each of the dimensions, and then they have like a linear layer on top of that to mix them. So that's just like one component, and that's why they say at the end of the paper that they're focusing on, like, one of the great extensions would be to figure out how to make this multidimensional. So you're not going from 1D sequences to 1D sequences and still get all the math that they're using to work. So yeah, I think that's a good start off. And yeah, we'll start here, just like jump into the method. And the method itself, it relies on like, what would I call it? The underlying components of the method are two things. The first one is this thing called a, they call it the fundamental state space representation. I actually feel like having a bit of a background in controls, that I can see why they describe it that way, but it's actually, there's a lot more detail to it. And there's a really great reference, which is this thing here called the annotated S4, like it's a I think a README. And I'm just gonna post it in the chat because I found it to be super helpful, and it has code in JAX, which is really cool as well for like all the parts of it, which you can just copy and paste and it probably just works. But this gives like a better like nitty gritty explanation of everything. And it's, for example, for additional detail, this is a linear time invariant state space representation of a system. And the reason why it's called a state space representation is because your state is X, and then you have some actions U, which either you choose or the environment chooses for you. And then you have some like, you have some like state, and then you also have some output or like impact of the state at each point, which is Y. So there's like action is U, X is state, and Y is like some output that you're trying to predict. And in the case of the math in this problem, U is the input sequence and Y is the output sequence, and X is a hidden state space of some dimensionality which you choose. So I don't think X has to be one dimensional, but maybe it does. I'll have to look it up. Over here in the notation, it seems like it has to be one dimensional. And so you're making a lot of simplifying assumptions with like linear time invariant state spaces, but the way that these models are used, it seems like there might be a question. Sorry, I missed it. No, it's not. Oh, Alexander, what do you mean? No, it's not. If you can type.
Sorry, yeah, I think so the hidden state is can be like high dimensional or something, right?
Okay, yeah, you're right. It even says it here. My bad. It says ND dimensional latent space. So yeah, you're right. Thanks. And so in terms of control systems, when you say linear time invariant, it means that like the transition function, or when you go from one state to the next, you can express it as a linear function. And then time invariant means that it's the same transition matrices, because by being able to express it as a linear function, you can take your state and multiply it by a matrix to get, like in the continuous case, your velocity, like the change in your state or the rate of change in your state. And then it's the same at each time step, which is just like YA is constant. that makes more sense to me in the case, in the context that they're using it, because they're not actually trying to model physical systems, and each layer is independent of the next. So in the sense that you learn multiple layers independently of each other. So it's not like you're applying this transformation over and over again. Well, actually, you are applying it over and over again throughout the whole sequence. So anyway, like it's taken from trying to model physical systems, but it's not really used in that context here. I'm sure there are problems you could apply it to, like maybe the weather forecasting problems in the experiments. But in general, X is considered a hidden state. So it's not like a physical state. Like, for example, like the position and velocity of a projectile or something like that. And another key thing about this state space representation, the one that they're using, and I think all, is that you can represent it in three ways. You can represent it in continuous space, which is when you're operating on like functions. And then you can discretize it. So say you have X is some continuous function in your in some domain. Instead of having like operating on X, you can say like, I'm just going to sample from X every like second if it's a time dependent system, and then you'll just get discrete points, and you can actually create a discrete representation of your system and calculate like the equivalent matrices, which is like A with the bar on top, B with the bar on top, and so on. Sorry about that. It seems like there's like an alarm that went off outside, but hopefully it's not too distracting. And so you have your continuous representation, your discrete representation, and then you have your like frequency space representation. So the other two, you kind of are viewing them as if they're in with time, but the other one isn't with frequency, so 1 over time. And a lot of the math that they use for their methodology relies on the fact that you can go between these two, these different representations, and specifically go between the, I really hope that stops soon, go between the discrete representation and the frequency domain discrete representation, because that's where you get some of the computational benefits and memory benefit, well, more computational benefits that you don't get with other models. So that's the state space representation and some background on it. The other thing that they use is that they use this thing called a Hippo Matrix, which is, there's a lot of cool math around it, which I don't know. But I looked it up a little bit so I could give a good explanation. And essentially, so it's the idea behind the Hippo Matrix is that if you are, if you model your system with this like linear time invariant state space representation, like the one in equation 1, and then you use a Hippo matrix for A, then by propagating through your system with it, you can actually memorize your somehow memorize your inputs U. I'm not giving a great explanation, but I'm hoping that this diagram will help. So and maybe the explanation they have there, where is it? Okay, so yeah, the Hippo matrix has a very specific form, and it was literally designed, and it has like the mathematical proof is around the idea of continuous time memorization. And it essentially, what it means is that it says it over here, Hippo specifies a class of certain matrices A that when incorporated allow the state X to memorize the history of inputs U. So that's why this matrix is really powerful, is because you can literally memorize the inputs of the inputs that you started with, which means that you can, your state, like your hidden state, will actually from it you'll be able to actually what's it called? You'd actually be able to reconstruct your inputs, which means that you could get information that's like 16,000 steps behind, because that's what this matrix is designed to do. And the reason why, if anyone wants to know, is essentially what this matrix does is it encodes the inputs, the input function, using these types of polynomials called Legendre polynomials, and it saves the coefficients of, like if you were to represent the input function as a linear combination of Legendre polynomials, like and it would just be like your basis would be Legendre polynomial of like 0 to L, where L is your sequence size, then it would like this matrix will calculate the coefficient that you need for each of those terms in order to memorize that sequence. So that's why it's used, because it can literally memorize the inputs, which means that you're definitely able to capture long-term dependencies, because you're able to fully describe your entire input sequence, which is not something that you could do with like guarantee that you're doing with a lot of other matrices that you might use. So those are the two fundamental ideas, like state space representation and Hippo. As like essentially what they do is they initialize your A matrix as the Hippo matrix in their method. This I'm not going to go into a lot of detail about it, but I'll just say that, so like here's the discrete space representation we were talking about, and then here's the convolutional, and one of the main ideas behind what makes this computationally efficient is, oh, there's another thing in the chat. Can we say the Hippo matrix is a projection on the base of I'm not sure what the terminology is in terms of, oh, is it a projection? Yeah, I'm gonna have to, Alexander, I'm gonna have to go with like, I'm not sure, unfortunately here, because I just read a little bit into it. I wish I could give you a better answer, but I would, if you want to look into it, I would look into this website, because it has a lot of like, that I posted, because it has a lot of like references to different parts of the math that's used here. But so, like I said, there's the two representations that they really use, which is the discrete, oh, there's another, okay, yeah, no problem. There's the discrete time state, the discrete representation and the convolutional representation of the discrete time. And the key thing about it is that, the key thing about it is that if you were just to use the discrete time representation of this state space in order to propagate through your sequence, to go from one sequence to the next, you would have to go through the whole sequence one at a time. So you'd look at the first step, and then the second step, and the third, which means it's not parallelizable, and that makes it highly computationally inefficient. And so it would be like on par with recurrent neural networks or LSTMs. But that's not great, because we want something that that's computationally efficient. And so the reason why they introduced this like convolutional representation, which is the frequency space representation, is because then you can represent the operations you're performing as a convolution, which means you can perform them all at once at the same time. So essentially it's a parallelizable calculation. And that's why using this representation in order to do the calculations in the layer is more powerful. But there's a problem with all of this, which is that where does it say it? Okay, so the problem with all of this cool math up to this point, which is like the basis of it, is they say it over here. So in order to perform the convolution, you need this matrix K bar. And it says, however, computing K bar in 5 is non-trivial and is the focus of our technical contribution. And we call K bar the SSM convolutional kernel. So, and one cool thing about all of this is that, I never mind. Like this is pretty cool, but we'll go over it a little bit later. So yeah, the whole thing that they focus on is like, is there a way for us to compute K quickly? Because if we can compute K quickly, then we can use a convolutional representation of our system, and then we can calculate everything super quickly, and we get all the computational benefits that we want. The representation itself already gives you a lot of memory benefits because it's very low. It doesn't require a lot of parameters to express a layer, because everything's like 1D and blah blah. But this is where this is why this is a contribution, because it's about like how can we do things quickly. And there's a lot of math here, which I don't want to go too far into, but I kind of want to give like a sketch of why they're doing what they're doing. And so let's start off with there's these type of matrices that are called normal matrices. And I'm pretty sure that a normal matrix is one where it's like inverse is just it's negative, but I have to remember. I don't remember. We can check really quickly.
Isn't it like a matrix which commute with this dual?
Oh yeah, but let's just look it up because they have it. Or we'll look it up here. Yeah, so it commutes with its conjugate transpose. That's it. But like I think that the key part of it that they use is that is over here. It's unitary. It says like the spectral theorem states that a matrix is normal if and only if it's unitary, similar to a diagonal matrix, and therefore any A that's satisfying this is diagonalizable. So you can transfer it and it's diagonalizable, or you can perform some linear operations and it's diagonalizable. And that's actually important. Maybe I should say this because of this proof here, which is conjugation is an equivalence relations for structured state space models. So I guess the first step in their methodology is they show that you can conjugate the system and still get the same results. And that's important because then you can take like the matrix that they're going to describe later, conjugate your system, and get like a diagonal matrix or diagonal plus low rank, and do all this cool math. So anyway, first step, you can conjugation is an equivalence relation on structured state spaces. Second step is different ways we can represent these normal plus low rank matrices. So again, I don't want to go into all of this. I'm just going to show you at the end what the result of it is. And I would encourage, if you want to like actually understand it, which I think takes a while, like I think I'd have to read the paper a couple more times to understand everything. I would also, that website is really good, but essentially you can represent a normal matrix as a, where is it? Normal plus low rank. You can they're saying like you can represent an A matrix as a normal matrix plus low rank. And they say, oh man, I'm really butchering this explanation. What should I talk about? Yeah, I'm not going to go through all of this because it's a lot. But essentially what they show is that if you if you can represent your A matrix as a normal plus low rank matrix, which is this here, then you get a really cool situation where you can take your input sequence and multiply it by something you calculate and get your output sequence. And it's basically what they say over here is that there's in the case of a diagonal matrix, like if you could represent your A as a diagonal matrix, then you would be able to calculate something called a Cauchy kernel. And the Cauchy kernel, when you want to figure out what your output sequence is, you just multiply your input sequence by like the terms in the Cauchy kernel up to like the length of the sequence. In this case, all their math, what it does is it shows that you can calculate K and it reduces down to 4 Cauchy multipliers. So if we look in the web, in the annotated, make sure there's no comments. Oh, there's someone who, if we look in the code, where is it? I think it's farther up. Yeah, okay. If we look in the code, because I think it's helpful to look at the code because it just helps. Basically, what C is like a frequency domain representation of your input sequence. And then you can calculate these Ks, which are the Cauchy kernels. And you can calculate this and multiply it by your input sequence and then do an inverse fast Fourier transform to get your true output sequence. And the whole point is that all you have to do is multiply your input sequence by like another vector, and it's an element-wise calculation, like multiplication, and so it's super quick. Yeah, if we go really deep into the math, I think I would have to spend maybe like a couple of days presenting a presentation that actually does it some justice because it's all super cool. But that's what it boils down to. Like, they found a way to express to do this calculation really quick to figure out what the output sequence is based on their model. And like a key other step for anyone who does want to go into the math is that they're able to show that you can go from a Hippo matrix to like a normal plus low rank matrix. Yeah, this theorem here. That's really important because all of their math relies on the A matrix being able to be expressed as a normal plus low rank matrix. And I think it relies on it being a diagonal plus low rank matrix. But because normal matrices can be expressed as diagonals, there's a lot of different steps in here. Anyway, and so yeah, that's all this really cool math. What it's telling you is that we can do something really computationally efficient, which is this here. It's like we can calculate the output sequence in this with this computational complexity. Yeah, and then they talk about the layer that they're actually proposing in this problem. So the layer that they're actually proposing in this problem is, so like I said, here, this goes from a 1D input sequence to a 1D output sequence. So from U to Y. And the layer that they're proposing is that, say you have an input sequence which is a multi-dimensional, so maybe like language embeddings. What you would do is you would have one of these, like a set of matrices A, B, C, D, or like the representation they use for each dimension of your vector for your sequence. And then you would have on top, you would perform all the operations we talked about, so to go from U to Y. And then you would have a linear layer on top of that, which would mix the different dimensions of your input sequence, because since this only goes from 1D to 1D, there's no like looking at the dependencies between between features when you're trying to learn a model. So they have a linear model on top of that, and then they have a activation function, I think, on top of that. Let's see. Yeah, they have a linear transformation. Yeah, I'm pretty sure that they have a like a ReLU or some nonlinear activation function, and then they said in some follow-up work they added dropout. And I think the implementation that they have on that website uses dropout afterwards as well. So all of this cool math is just for that one component of one layer, and they're saying like you can take many layers in order to learn like a deeper model. So let's talk about all the a very comprehensive set of experiments, which were actually pretty good. Like I think that's what another strength of this method is that they just did so many experiments and got great results. So yeah.
So what are the learnable parameters for the layer?
Okay, so the learnable parameters are so this is, first of all, they in all of their math, they assume that, remember how we said that D is like part of the state space? They assume like that you can exclude D because it's a skip connection, or you could just add in a skip connection, and so D is not learnable. So instead, the learnable parameters are L, which is this diagonal matrix, P and Q, which are two vectors actually. B, so actually an L you can represent as a lambda you can represent as a vector, and then B and C. So those are the learnable parameters of the model from this layer. But then on top of that, you have that linear layer that they use for mixing that you can also learn. So those are the learnable parameters of each layer.
Okay.
And so let's talk about experiments. So the first set of experiments that they run are, let's see. Okay, so yeah, we'll just go through all of the tables one by one. I think that's a good way to do it, because you don't really need the other stuff for it. Anyway, so the first thing that they do is they calculate how much more efficient their method is than using like the linear state space. I don't know what the other L stands for. But anyway, this is the method that this paper is based off of, but they found a way to make it more computationally efficient. And what they show is that their method scales much quicker, like much better in terms of like training time. So basically computational cost than the previous method that this is built off of. Like you can see that you get major gains as you increase the dimensionality of your input sequence. And then the other thing is also true of your of memory allocation. Like you get much better, you use up much less memory as the dimensionality of your inputs increases. So this is just showing you that you get better. Like the efficient part of the title is true. But what they also do is they want to show how it does against transformers. So they do the same calculation versus transformers. And they show that they're more memory efficient essentially, but they're actually a little bit slower for calculation. Yeah, so more memory efficient with comparison with transformers, less time efficient. And then the next set of experiments is on this long range arena. So this is where they're testing, like, does this model outperform other models in terms of like finding, in terms of tasks that require identifying and inferring based on long range dependencies. And if you look at all of the tasks, you can see that their method performs better than the previous ones, like the ones that claimed state of the art on this before. And what's interesting is that no other method has even been able to accomplish this path X task, whereas this method has. And I think it describes what the path X it says example from PathX task, which involves deducing if the markers are connected by a path. So if this is connected to this. So yeah, and yeah.
So there's a path task with a low resolution image, and the path X is for like twice the resolution. And so I think the path X, because the resolution is higher, is for longest sequence, I think. Something
Yeah,
like
it's a long sequence because they actually view images as one, like they flatten images as a 1D vector.
yeah.
So you'd have to sometimes, like depending on where the dot is, it could be, if it's like on opposite ends of the image, it would be a very long dependency.
Yeah, and so there's a path task which has a lower resolution, so it's shorter sequence.
Ah, okay.
Yeah, but yeah.
Is that the Pathfinder?
Maybe I don't remember the name, but yeah, could be.
Okay, that's good to know. So yeah, in terms of learning long-range dependencies, they do better. I'm not going to go over this one because I really like this ablation study they do later where they test how good their model is in terms of experiments. But the next thing they do as a test is they want to show like, okay, we've shown our model does well long-range dependency tasks, but what about just on general sequence tasks that we use as benchmarks? And what they show is that they can apply their model to a lot of different benchmarks, where here's like speech classification. This is image classification when you're viewing the image as a vector, and they get near or state-of-the-art performance on all of the different data sets where you would use this method. So it's good in speech classification and it's good in image classification. So they've shown that it works well in 2 domains based on common benchmarks. And one point they make is that you don't even need to have these like hand-designed features, which are what MFCCs are, like they're heuristic features in order to perform, like to get good results. In fact, it seems like you get better results without them. Oh, and then so they've shown that it works well on different tasks, and then they look at generative modeling, and they show that I think their method has. Oh, I guess it doesn't have. No, that's pretty good, right? Oh, it's lowest is better. So bits per dimension is like the lower that is, the better, and that's for that's like in some way related to log likelihood here. So in CFAR 10 density estimation, their method is definitely faster, but it gets close in terms of likelihood to the best performing model, which is this like sparse transformer. Yeah, and then they also tested on language modeling, and they get not as good performance as a transformer, but pretty good, like better than all of the other models, which I guess are supposed to be more computationally efficient than a transformer. So that's language modeling. Yeah, let's move on to the ablation studies. So, and I don't really even have to, I don't have to go through the text. I can just show you these charts because I think they're a good way of looking at it. So over here, they have, they use, one of the things they want to test is because as I said, one of the key ideas behind it is using this Hippo Matrix, which can like explicitly, you have like a proven guarantee that it can memorize long sequences, input sequences, is using this matrix versus using a randomly initialized matrix or a diagonal matrix useful, and then is training this the matrices in your state space useful. So in each of their layers, they have like the state space matrices that are used, but there's also that linear layer on top. So in all of the cases, they're always training that linear layer on top, but in the dotted line cases, they're not training the state space representation, the state space matrices, they're just training the linear layer, and in the solid line, they're training the linear layers, the matrices as well. So that's the difference between the two. And you can see that they're showing like train accuracy versus val accuracy. And you can see that like the Hippo Matrix, even without training, actually performs pretty well. But with training, it performs well, like a little bit better. And what this chart shows that in terms of generalization, using the Hippo Matrix definitely gives you a big, like a jump in performance that is important. And then over here, I think they just are comparing like, let's see. Right. Oh, this is, let's see. I'd have to read through the experiment, but this is this experiments again. Essentially, these charts are a good way of showing that all of the different components of their method have an impact and are important, which is good, because you don't want unnecessary details in here. And one cool thing I think about this whole method is that it doesn't have a lot of I don't think it has any hyperparameters. Alexander, I just realized that I forgot one trainable parameter that's important, which is here, the step size. So they actually also learn the step size that they use to go from the continuous representation to the discrete representation. That's one of the things they learn. Yeah, so that's the paper. Like it said, the experiments show good at long-range dependency tasks, good general sequence model, either close to or on par with like the best performing models in terms of sequence to sequence tasks. And the results suggest that all of the, like both using the Hippo matrix, training your layers and training your state space matrices, and using the state space representation, all of that is important for getting good results. So yeah, that's the paper. I'll stop talking because I've been talking for way too long. If anyone has any questions or things they want to talk about, feel free to mute yourself and ask now.
Are there any assumptions on periodicity of the input? Like, do the signals repeat? Like for a Fourier transform, you assume that the piece that you've sampled repeats forever. Is there any similar assumptions that you saw?
I don't think so. I think to figure that out, you'd have to go pretty deep into the math. But no, I don't think so, because I think part of it is like that's true, but you can always like increase the period of your function. So even for your functions, like if you have a bounded domain, can express any function, and maybe the implicit assumption is that the function has a bounded domain, which is also true for using the Hippo matrix. Like Legendre polynomials actually only operate, they're only defined, or they're for -1 to 1. Like
excellent. That's what I'm asking. Excellent. Yeah. Okay. Great. Yeah.
But if you have a function that's has a domain of like -1 to 1, you can make it any bounded interval by just rescaling it.
Absolutely. Okay.
Yeah, I think that personally, I thought this was a really cool paper because as someone who studied robotics, you actually learn all of this stuff. Well, not all of it, but a lot of it in control classes. And so there's probably, like, including me, thousands and thousands, if not tens of thousands of people who have learned this and never thought of going down this route with it. So whoever was working on this paper just made a really creative connection in terms of applying control theory to like a general problems, which is sequence to sequence modeling, and has a really good background in linear algebra as well.
I noticed they say they've got all their code published as well, which is great.
Yeah, and like this whole I mean, you have to use JAX for if you want to use this code, but like all this code, you could just copy and paste it, I think, and you would be able to train your own version of this model. And what's nice is that unlike a lot of code that comes out of this is my personal opinion, like a lot of code that comes out of TensorFlow or PyTorch, which is written in a way which is often hard to understand.
Yeah.
In terms of like what actual calculations are being performed, because there's so much abstraction and stuff like that and commenting and stuff like that goes into it. This is like, it's so obvious what calculations are being done in each function, which is nice. Yeah.
I'm working on speech recognition at the moment, which is a 1D sample, like by definition, postcode modulated, and I'm really tempted. Yeah, anyway.
Yeah, maybe. Who knows? It could be like a really good application. It would be cool if you started seeing this in industry so soon. That would be such a major validation that this is a good method. Yeah, and they have shown that it performs well on a lot of complicated tasks. Like, I think speech tasks are quite complicated because of the noise involved in measurement and stuff like that.
Are brutally complicated for that reason, and the variability of they call it dynamic time warping. Each time I say the same word, if everything else is the same, I can just take a little bit longer to say it. And just from that point of view, it's brutally hard.
Yeah, the other interesting component of this could be maybe like an easy extension would be looking at sequences that have different cadences that are about the same environment and adding them together. That could be cool.
So financial markets have again 1D price, 1D function. But if you're looking just at the prices, but what they do is they have risk on and risk off days. So if you're looking at the prices, all of a sudden, New York comes on stream while London is on, and so you've got this periodicity going on. But then all of a sudden, one day, there's modal. Some days it acts like this, and other days it acts like that, and they have some of those periods you can easily capture because you know what's going on. Other times you don't. It's a bull market. It's a bear market. Yeah, very interesting.
Yeah, I like that you gave two good examples of where this could be applied in real life. Yeah, just to show that this is a really generalizable paper.
Yeah.
Cool. If there's nothing else, then I'll stop sharing my video. Wait, that's not the right video. Where is it? Stop share. And then I'll stop recording.